All right, hello everybody. I wanted to talk about a way to solve a differential equation numerically. And so this is a little different than in the previous videos where we found an exact formula that gives the solution. This is an approximation of the solution, and you are basically using the idea of tangent lines, of just little short, straight tangent lines to approximate what the function is actually doing. So, really, a lot of the big concepts in calculus are just taking curvy things and imagining that they are a bunch of little straight lines put together one after another. So, for example, if I just looked at a function like this, it's obviously not a line. There's a lot of curvy parts, but I can sort of pretend that it's a bunch of line segments. All of these line segments are straight lines, and just sort of tack them on one after another like this. And it's going to be pretty close to what the actual values of the function are. And what I'm doing is I'm trying to just tack one line on where the last one ended and make each line match up with the slope of the function. And that's really what we're doing in a lot of calculus, is breaking something down into little linear segments. If you think about what we're doing with integration, we're breaking them down to little rectangles, which are little linear shaped objects anyway. So let's look at an example of something that we could solve, but that we can also approximate. So for example, if we had, I guess I don't think Desmos will do it. Maybe it will. If we had a differential equation, something like dy dx equals, oops, I'm going to pause for a second. Okay, sorry about that. So if if we've got a differential equation like dy dx equals, we'll do something that is pretty easy to integrate actually. Let's just say it's y times x. This one turns out to be separable. You just divide by y on both sides and multiply by dx on both sides, and then you get natural log of the absolute value of y, x squared over 2 plus c. Now, let's say that there is a nice initial condition like y of 0 equals 1. If y of 0 equals 1, and I substitute that in right there, then I get natural log of 1 equals 0 squared over 2 plus c. In other words, c is equal to 0. And so this was one that we were able to solve analytically, and I'll write it up here. We're going to get y equals e to the x squared over 2. So I just raised both sides to the e here, and c was equal to 0. Let's say, however, that you didn't want to solve that, or you just had a brain fart and didn't recognize, oh, that's a separable differential equation. What you can do is numerically approximate it by using little tangent lines. So we have our initial condition, and we have our derivative. And our derivative tells us what the slope of the tangent line is at any given point. So I can plug in x equals 0 and y equals 1 to my derivative. And so what I'm going to do is kind of make a little list of derivatives here. dy dx at the point 0, comma 1 is just 1 times 0, which is 0. So what this means is that at the point 0, comma 1, I have a little flat tangent line like this. Now, what I need to decide is how many different lines do I want to do? Maybe I want to do lines that are the shorter, the better in general, but there's also sort of a balance. Like, I don't want to do lines that are only 0.0001 units long, because then I'm not going to get very far with my approximation. So maybe my goal is to get to x equals 2, and I will use lines that are 0.5 units long. It's not going to be a great approximation. As you add more lines, you get a better approximation. But just so the video is not 20-minute long video, I'm going to use 0.5 as the step value, as the length of my line. So what I'm going to do then is I'm going to use this tangent line, and I'm only going to use it for a step value of 0.5. So I'm going to start at 0, and I'm going to go to 0.5, which is just one of those boxes right there. So now where I'm at is I'm at the point of 0.5, comma 1. So I use 0.5 and 1 in my slope. Remember, the slope is just y times x. So 1 times 0.5 is 0.5. So now I'm going to actually write an equation of a line. At that point, the y value is 1, the slope is 0.5, and the x value is 0.5. I'm using point slope form, which, if you need a reminder, point slope form y minus y1 is m times x minus x1. That line right there, I'm going to go 0.5 units over, and I'm going to point a slope of 0.5. So it's going to go up like this, right here. Okay. At the next value, I'm going to get to, I'm going to go up another 0.5. I'm going to be at x equals 1. So if I plug in x equals 1, I get y minus 1 equals 0.5 times 1 minus 0.5, which is 0.25. So if I add 1, I get 1.25. And so remember that this was when x is equal 1. X is equal to 1. So this is now my next point that I'm going to plug into my derivative. So dy dx of 1 comma 1.25 is 1.25 times 1. So now my slope from there is 1.25. So I'm going to go slightly up. I'm going to go up slightly over, more than one box over, like that. So then I know that to find the value when x is 1.5, I'm going to create another tangent line. So my tangent line is y minus 1.25 equals the slope times x minus 1. And I can plug in the next point I care about, which is x equals 1.5. So y minus 1.25 equals 1.25 times 1.5 minus 1. And that gives me y minus 1.25. 1.25 times 0.5. Starts to get really annoying to do the calculations by hand, but I think that one I can still do. That's 0.625, and then add that, so I get y equals 0.625 plus that gives me 1.875. And then this will be the last one I'm going to use to approximate the value at x equals 2. So I go dy dx. My x value now is 1.5. My y value is 1.875. I'm going to multiply those. Oh yeah, I'm going to grab a calculator for this. So you multiply those together, and you get 2.8125. I'm going to use that to build one more tangent line. Y minus the y value we just got, 1.875, equals the slope value we just got, times x minus the x value we just used of 1.5. If I plug in 2, then I'm going to just have this number here times 2 minus 1.5, so that's 0.5. And then if I add 1 to that, if I add 1.875 to that, you can see what I did on the calculator there. I did times 0.5, then added 1.875, and I get y equals 3.28125. So I know I'm going to hit right about, let's see, this is 3, this is 3.5, so right about there. So that's my last tangent line right there. So it predicts that when x equals 2, that the y value is 3.2812. So what I'm going to do now is I'm going to type in the actual function, because we could solve this. Oops, it's not squared, it's e to the x, come on, x squared over 2. And you can see that my tangent lines are always an underestimate of the curve, but that it does tend in about the same direction as the red line. And I hope you can also see that if I used a smaller step size, instead of using a step size of 0.5, that I would get a closer and a closer approximation to the curve. This curve has a pretty steep rate of change, and so it goes away from the linear approximation really quickly. That's why that gap is growing and growing and growing. But a smaller step size will hug tighter and tighter and tighter to the red curve. And so this video was just trying to give you an idea of what Euler's method is and why it makes sense, that it is just using little lines as a way to approximate the solution to a differential equation and then comparing that to the actual analytic solution. So please comment if there's anything confusing, and I'm happy to help out.